Welcome back, everyone. Today, we're taking a deep dive into something pretty mind-blowing.
Oh, yeah.
Physics-based machine learning.
Yeah.
You know how AI is usually all about crunching numbers and spotting patterns. Well, this is about taking things to a whole new level,
Right.
teaching AI to actually reason about the physical world around us.
Mm.
We're talking about the research paper, Denoising Hamiltonian Network for Physical Reasoning.
It's a fascinating approach because it's not just about mimicking what we see.
Right.
It's about AI understanding the underlying laws of physics, how objects move, interact, the whole shebang.
Right. It's like giving AI a crash course in Physics 101.
Yeah.
But instead of textbooks, it's learning from data.
Yeah.
So walk us through this. What is a denoising Hamiltonian network, or DHN for short?
Well, DHN is all about combining the strengths of neural networks with a powerful tool from physics called Hamiltonian mechanics.
Okay.
You see, physicists use Hamiltonian mechanics to describe how systems evolve over time based on their energy. It's about understanding the forces at play and how they shape a system's trajectory.
Okay. So it's not just about looking at a snapshot in time.
Right.
It's about understanding the whole flow of energy in motion.
Exactly. And DHN leverages this by looking at blocks of system states,
Okay.
which include both the position and momentum of the system at various points in time.
Yeah.
This allows it to grasp those complex, longer-range interactions, just like a physicist would analyze a system in motion.
So it's like DHN is watching a movie of a physical process.
Yeah.
Instead of just looking at a single frame. It's getting the whole story, not just a snapshot.
Precisely.
Yeah.
And here's the really ingenious part, the denoising aspect.
Okay.
Think of it like this. Noise reduction cleans up images, right?
Right.
DHN does something similar for its understanding of physics.
Okay.
It constantly refines its predictions,
Yeah.
ensuring they align with the laws of physics, leading to more accurate and stable results over time.
So it's not just making guesses. It's double-checking its work to make sure it's consistent with the laws of physics.
Yeah.
It's like having a built-in physics tutor.
Right.
But tell me, this DHN, it can do more than just solve textbook problems, right?
You're absolutely right. That's what makes this research so exciting.
Okay.
DHN has the potential to go way beyond that. Think predicting how a system will behave in the future, essentially running a simulation.
Okay.
Or imagine it filling in gaps in incomplete data, like reconstructing a damaged film reel.
Wow.
It can even uncover the hidden rules governing a system just by observing it.
Wow. It's like DHN has become a detective of the physical world, predict the future, reconstruct the past,
Right.
and even deduce the underlying laws.
Yeah.
How did they put these amazing claims to the test?
Well, the researchers devised 3 specific tasks for DHN forward simulation.
Okay.
Representation learning, which is all about figuring out the hidden parameters of a system.
Right.
And trajectory interpolation, filling in those missing pieces of the puzzle.
Okay, so they've set up the challenges, the physics exams, for our AI prodigy.
Right.
But what was the classroom like for these tests?
They chose simulations of pendulums, both single and double pendulums.
Pendulums? That seems a bit basic, doesn't it? Like Physics 101 stuff.
Well, you might be surprised. Pendulums are a deceptively simple system.
Okay.
They're familiar, visually interesting, and their motion, especially in the case of the double pendulum, can get quite complex.
Yeah.
Plus, they provide a clear way to visualize and understand the underlying physics.
So it's like the fruit fly of physics experiments, simple yet insightful.
Yeah.
But I have a hunch they didn't just use one standard pendulum for all the tests, did they?
You're catching on. They actually varied the lengths of the pendulums in their experiments.
Okay.
This was crucial to see if DHN could truly generalize to different physical systems, not just memorize one specific setup.
Right.
They wanted to know if it could handle different flavors of pendulums, so to speak.
That makes sense. So how did DHN perform on its first big test, the forward simulation challenge?
In forward simulation, DHN was given some initial information about the pendulum, like its starting position and momentum, and then tasked with predicting its movement over time.
Okay.
And I have to say, it performed remarkably well.
So it basically predicted the whole movie of the pendulum swinging
Yes.
just from seeing the first few frames.
Exactly. And it wasn't just about getting the general movement right.
Okay.
DHN also maintained energy conservation throughout its predictions, which is incredibly important for creating realistic physics simulations.
Right, because energy can't just magically appear or disappear, even in a simulation.
Right.
That's breaking the fundamental laws of physics.
Exactly.
But was DHN just lucky, or did it actually outperform other methods?
It wasn't just luck. They compared DHN's performance to a standard Hamiltonian neural network, or HNN,
Okay.
which doesn't have that denoising component.
Right.
And DHN consistently came out on top, especially when making predictions further into the future.
Wow. So DHN aced its first exam with flying colors. It can predict the future of a physical system
Yes,
while obeying the laws of physics.
it can.
But what about this representation learning task? Can it really decipher hidden properties just by watching a system in action?
That's where things get even more intriguing.
Okay.
For this task, DHN was trained to encode information about each pendulum system into a latent code,
Okay.
a kind of compressed representation of the system's key characteristics.
Right.
Like DHN is creating its own language to describe the pendulums.
So it's not just mimicking, it's actually developing an understanding, a representation of what makes each pendulum unique.
Precisely. And the researchers wanted to know if they could decode important physical properties from these latent codes.
Okay.
They focused on the length ratio of the double pendulum. Could DHN figure out the relative lengths of the two arms just by analyzing the motion?
Okay, now I'm on the edge of my seat. Did DHN crack the code?
The results were surprisingly good. DHN successfully figured out the length ratio of the double pendulum just from its latent code.
Wow.
This indicates that it can actually learn meaningful physical properties directly from raw data without being explicitly told what to look for.
That's incredible. It's not just mimicking motion, it's extracting real physical understanding from what it observes.
Yes,
Like it's reverse engineering the system to figure out its blueprints.
it is. And that brings us to the final challenge, trajectory interpolation.
Okay.
Imagine a movie reel with missing frames.
Yeah.
Could DHN fill in those gaps convincingly and in a way that's consistent with physics?
Okay, this sounds like a real test of its abilities.
It is.
How did they set up this challenge?
They trained DHN to upscale scarce trajectory data.
Okay.
Essentially, it had to take a limited set of data points describing the pendulum's motion and fill in the missing pieces to create a smooth, complete trajectory.
Okay.
It's like taking a blurry, incomplete picture and using AI to enhance it, but with a focus on physics.
So, did DHN manage to reconstruct the missing frames in a way that made sense, physically speaking?
The results were very promising.
Yeah.
DHN successfully interpolated the missing data, creating smooth and physically plausible trajectories.
Okay.
It even outperformed a standard convolutional neural network, or CNN, which is a powerful tool often used for image processing and analysis.
Right.
And what's even more impressive is that it did this even when tested on trajectories with starting conditions it had never seen before.
So it's not just better than a basic physics engine, it's outperforming some of the heavy hitters in AI.
It is.
This suggests it's not just memorizing patterns, but truly learning the underlying physics,
Right.
allowing it to adapt to new situations.
Exactly.
This DHN is something else.
It is. And it highlights the incredible potential of combining data-driven learning with existing scientific knowledge.
Okay, so we've seen DHN predict the future, reconstruct the past, and even deduce hidden properties.
Yeah.
It's like it has superpowers. But let's step back for a moment
I like
and
it.
look at the bigger picture. Right.
What does this research really mean?
Well-
Where does it fit into the grand scheme of things?
That's a great question.
Yeah.
This research signifies a significant step towards creating AI that can genuinely understand and reason about the physical world,
Okay.
not just process data.
It sounds like we're at the cusp of something truly groundbreaking.
It does.
But I'm curious, what are the limitations of this approach? What hurdles do we still need to overcome?
That's a great point.
Yeah.
Every groundbreaking advancement comes with its own set of challenges.
Right.
And DHN is no exception. For instance, DHN still relies heavily on data for effective learning. We can't just point it at any physical system and expect it to miraculously figure everything out.
So it's not a magic bullet. It still needs guidance and training.
Exactly. And that training process itself can be computationally expensive,
Right.
especially as we move towards more complex systems.
Yeah.
Imagine trying to simulate the weather or the behavior of a galaxy. The amount of data and processing power required is immense. So scalability is a concern, but given how fast technology is evolving, it seems like it's more a matter of when, not if.
I tend to agree.
Okay.
Another limitation is that DHN primarily focuses on classical physics.
Right.
This means it excels at systems governed by laws of motion and gravity. But what about the quantum world? Things get a lot weirder at the quantum level.
Right. Quantum physics is a whole different ballgame. with its own set of mind-bending rules.
Exactly. Incorporating those principles into a system like DHN is a whole other challenge, but a fascinating one.
Right.
There's already some incredible research happening at the intersection of AI and quantum physics.
So someday we might see a DHN that can model the behavior of subatomic particles. The implications for fields like materials, science, and drug discovery would be huge.
The possibilities are definitely there.
Right.
What's truly exciting is that this research challenges our preconceived notions of what AI can achieve.
Right.
It's not just about recognizing patterns or automation. It's about comprehending the fundamental principles that govern our universe.
That's a profound thought. So as we delve deeper into this world of physics-based machine learning,
Yeah.
I have to ask the million-dollar question. What does the future hold?
I think the potential is limitless. We're just scratching the surface of what's possible.
Yeah.
In the coming years, I anticipate seeing incredible progress in areas like scientific discovery,
Okay.
engineering design, and even art and entertainment.
Get ready for AI-powered scientific breakthroughs, self-designing bridges, and video games that blur the line between reality and simulation.
Exactly. And who knows what other groundbreaking applications will emerge. That's the beauty of this field. It's constantly pushing the boundaries of what we thought was possible.
I'm definitely inspired to dive deeper into this, but before we move on, I want to leave our listeners with a thought-provoking question, something to ponder. What if DHN's ability to learn physical rules and reason about complex systems could be applied to something even bigger than pendulums or galaxies? What if we could use it to understand the complexities of human behavior or the dynamics of entire ecosystems?
That's an incredibly intriguing question. It takes us beyond the realm of physics and into the realm of social sciences, biology, even philosophy. If DHN can learn the rules of a double pendulum, perhaps it can unlock the secrets of far more complex systems.
Precisely. And who knows, maybe it could help us tackle some of the biggest challenges facing humanity.
It's definitely food for thought. And it underscores the potential of this research to impact not just science and technology, but our understanding of ourselves and the world around us.
That's a fantastic point.
Yeah.
We've covered a lot of ground in this first part of our deep dive, from the intricacies of DHN to the broader implications of physics-based machine learning.
It's been a fascinating journey so far, and I hope our listeners have gained a deeper appreciation for the incredible possibilities that arise when we combine AI with scientific knowledge.
I completely agree. Stay tuned for part 2 of our deep dive, where we'll explore even more fascinating aspects of this groundbreaking research.
Sounds good.
Yeah.
It's amazing to think we're at a point where AI can not only learn from data, but also learn from the fundamental laws of physics.
It really is a paradigm shift. We've been talking about how DHN can learn and predict,
Right.
but I'm curious about what's happening under the hood that allows it to make these incredible leaps.
Well, DHN represents a departure from traditional physics-based modeling.
Okay.
Previously, simulating even relatively simple systems required complex equations and immense computing power.
Right.
It was a very labor-intensive process.
I can relate to that. I once tried coding a physics engine for a simple game,
Oh, yeah?
and let's just say it was a humbling experience.
It can be.
Yeah.
That's why DHN's approach is so revolutionary.
Okay.
It demonstrates how AI can learn these complex interactions directly from data,
Yeah.
almost like it's developing its own intuition about the physical world.
Intuition is not a word you typically associate with AI.
Right.
We usually talk about algorithms and data crunching,
Yeah.
but DHN seems to be operating on another level.
It is. We're witnessing a shift from explicitly programming every rule and constraint to letting the AI learn these rules organically by observing and interacting with the world,
Okay.
much like a human child would.
So instead of feeding it equations, we're feeding it experiences.
Yeah.
That's a fascinating way to think about it.
Precisely. And the amazing thing is that DHN isn't passively absorbing information. It's actively trying to make sense of it,
Yeah.
to find the underlying structure and principles that govern the behavior it observes.
It sounds like DHN is doing what physicists have been doing for centuries,
Yeah.
just at an accelerated pace and within
Well-
a much larger data set.
Exactly. And that's precisely why this research is so exciting.
Right.
It holds the potential to accelerate scientific discovery in ways we can only begin to imagine.
So we've seen how DHN excels in its physics exams,
Yeah.
simulating, predicting, and even learning hidden properties. But let's take a step back and consider the bigger picture.
Okay.
What are the limitations?
Mhm.
Where might this approach fall short?
That's a crucial question.
Yeah.
Every breakthrough comes with its own set of challenges,
Okay.
and DHN is no exception.
Right.
One key consideration is that DHN still requires a significant amount of data to learn effectively.
Okay.
It's not a magical solution that can decipher any physical system without sufficient input.
So it's not a silver bullet.
Right.
It still needs to be trained and guided.
It does.
But are there other challenges?
Well, as we discussed earlier, the training process for DHN can be computationally expensive,
Right.
particularly when dealing with more complex systems.
Right.
Simulating something like weather patterns or the behavior of a galaxy would demand an immense amount of data and processing power.
So scalability is a valid concern.
It is.
But given the rapid pace of technological advancement, wouldn't you say it's more a matter of when, not if, we can overcome these limitations?
I'm inclined to agree. However, there's another limitation worth considering. DHN primarily focuses on classical physics.
Right.
It excels at systems governed by the familiar laws of motion and gravity.
Right.
But what about quantum mechanics?
Yeah.
Things get considerably more complex and counterintuitive at the quantum level.
Right. The quantum realm operates under a completely different set of rules.
It does.
It almost feels like magic sometimes.
It does. And integrating those principles into a system like DHN presents a significant challenge.
Right.
It's an open question, but there's a lot of fascinating research happening at the intersection of AI and quantum physics that might hold the key.
So we might one day witness a DHN that can model the behavior of subatomic particles.
We might.
The implications for fields like materials science and drug discovery would be revolutionary.
Absolutely.
Yeah.
This research challenges our preconceived notions of what AI can accomplish. It goes beyond mere pattern recognition or automation.
Right.
It's about developing a genuine understanding of the fundamental principles governing our universe.
That's an incredibly powerful thought.
It is.
It almost feels like we're on the verge of a new era of scientific understanding.
It does, doesn't it? What's particularly exciting is that DHN's success goes beyond purely scientific applications.
Okay.
Think about the potential in fields like engineering and design.
Right. We briefly touched on this earlier,
Yeah.
but I'd love to delve a little deeper.
Yeah.
What are some of the potential real-world applications outside of the research lab?
Well, imagine using DHN to design more efficient and robust structures, like bridges or skyscrapers.
Okay.
It could analyze structural integrity,
Right.
predict potential weaknesses,
Yeah.
and optimize designs in ways that were previously unimaginable.
That's incredible. It would revolutionize the field of civil engineering.
It would.
But what about other applications?
The possibilities are truly vast.
Okay.
Think about manufacturing, optimizing production lines,
Yeah.
predicting equipment failures,
Right.
and even designing entirely new materials with specific properties. DHN could accelerate the development of lightweight, durable materials for everything from aerospace to consumer electronics.
So this isn't just about understanding the universe, it's about shaping it.
It is.
But as we explore these potential applications, we have to consider the human element.
Right.
How might DHN impact the workforce? Are we talking about robots replacing human engineers and designers?
That's a valid concern and one that deserves careful consideration.
Okay.
However, I believe that tools like DHN will ultimately augment human capabilities rather than replace them.
Okay.
Think of it as a collaboration between human ingenuity and AI-powered insights.
So instead of fearing job displacement, we should view it as an opportunity to work alongside these powerful AI systems to achieve greater heights.
Exactly. By combining human creativity and intuition with DHN's ability to analyze vast data sets and make complex predictions, we can unlock a whole new level of innovation and problem solving.
That's a much more optimistic and frankly exciting perspective. It sounds like DHN could be a game changer in countless fields, empowering us to tackle some of the world's most pressing challenges.
It certainly has the potential.
Right.
And I believe that's what makes this research so compelling. It sparks our imagination and pushes us to reimagine what's possible.
This has been an incredibly enlightening conversation so far.
It has.
We've explored the inner workings of DHN,
Right.
delved into its limitations,
Yeah.
and glimpsed its vast potential across various fields.
We've only scratched the surface. There's still so much more to uncover about DHN and the broader field of physics-based machine learning.
And that's precisely what we'll be doing in part 3 of our deep dive. We'll delve even deeper into the implications of this groundbreaking research, exploring its ethical dimensions and potential societal impact. Welcome back to the final part of our deep dive into DHN.
Okay.
We've talked about its potential to revolutionize fields like engineering and science,
Right.
but with any powerful new technology, there are always broader implications to consider.
You're absolutely right. As we explore the vast potential of DHN, we must also consider the ethical and societal implications that come with such a powerful tool.
Exactly. And it's not just about potential job displacement,
Right.
which we touched on earlier.
Yeah.
There are also questions about responsibility,
Hmm.
transparency, and even bias.
Yeah.
If DHN is learning from data,
Right.
how can we ensure that the data itself isn't skewed or biased, leading to unfair or discriminatory outcomes?
That's a crucial point.
Yeah,
As with any AI system, DHN is only as good as the data it's trained on.
right.
If the data reflects existing societal biases,
Yeah.
those biases can be amplified in DHN's predictions and recommendations.
So it's not enough to simply marvel at DHN's capabilities.
Right.
We need to be critically aware of the data that's shaping its understanding of the world.
Precisely. We need to develop robust methods for auditing and mitigating bias in training data sets.
Right.
And this requires a multidisciplinary approach. We need ethicists, social scientists, and domain experts working alongside AI researchers to ensure that DHN and similar technologies are developed and deployed responsibly.
It sounds like this is where the conversation shifts from purely technical advancements to a more holistic consideration of the societal impact of these technologies.
Right.
It's not just about what DHN can do, but what it should do.
Exactly. As we venture further into the realm of AI that can reason about the physical world,
Right.
we need to establish clear ethical guidelines and frameworks for its development and application.
This raises a crucial question.
Okay.
Who gets to set those guidelines, and how do we ensure that they are inclusive and representative of diverse perspectives?
These are challenging questions, and there's no easy answer.
Right.
It requires open and transparent dialogue involving policymakers, researchers, industry leaders, and the public to establish ethical frameworks that are aligned with our shared values.
It sounds like we're talking about a fundamental shift in how we approach technological innovation. It's not just about building the most advanced tools,
Right.
but about ensuring that those tools are used for the betterment of humanity.
I couldn't agree more.
Yeah.
As we continue to develop increasingly sophisticated AI systems like DHN,
Right.
we must prioritize ethical considerations alongside technological advancements.
So what does this mean for the future of DHN and physics-based machine learning? What steps can we take to ensure that these technologies are developed and used responsibly?
Well, one important step is to foster interdisciplinary collaboration.
Okay.
We need experts from various fields, including ethics, law, and social sciences,
Yeah.
to work alongside AI researchers to address these complex challenges.
Right.
We also need to invest in public education and outreach
Yeah.
to ensure that people understand the potential benefits and risks of these technologies.
It sounds like this is about creating a dialogue,
Yeah,
a space where we can have these important conversations about the future we want to build with AI.
exactly. And it's a conversation that needs to involve everyone. After all, the future of AI is ultimately the future of humanity.
Well said. We've covered an incredible amount of ground in this deep dive,
We have.
exploring the technical marvel that is DHN,
Yeah.
delving into its potential applications,
Right.
and grappling with the ethical questions it raises.
It's been a fascinating journey, and I hope our listeners have gained a deeper appreciation for the power and complexity of physics-based machine learning.
I couldn't agree more. It's clear that DHN and similar technologies hold immense promise for solving some of the world's most pressing challenges.
Yeah.
But as we move forward, we must do so with a sense of responsibility,
Right.
ensuring that these powerful tools are used for the benefit of all humankind.
Absolutely.
Thanks for joining us on this deep dive into the world of DHN and physics-based machine learning.
It's been a pleasure.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible.